Okay, so just to recap. Second, bars. Get you to that menu. Okay, so on the county judge example, we were doing Z. So what kind of distribution does Z come from? Normal. So let's go down here to where it says normal CDF. What the CDF is doing is it's finding a cumulative area. It's finding our area. The PDF is just a specific value, which means nothing does. So we want the normal CDF. And let's hit enter. Now, for some of y'all, it'll come to this screen. Others, it'll take you back to a home screen where it just says normal CDF with open parentheses. Either way, you would put the numbers in the same order that we're about to put them here. So, on our paper, what did we say we wanted for the Z score? We wanted Z to be greater than what? On that example. It's going to be greater than 1.39, which means 1.39 is the lowest it could be, right? You want to be greater than that? So let's put that in for lower. 1.39. That's the lowest we can be. Now for upper, there is no bound, but we have to put something. So we're just going to put a really, really big, I say a really, really big. It's not really, really big, but 999. For the standard normal, that's pretty big. Leave the mean at 0 and deviation at 1. And then we're going to hit paste. Now, if yours took you to the home screen from the get-go and didn't even bring you to that screen, then you would enter in exactly what we have there with the commas. And the comma is above the 7. Once you get that, let's hit enter. And then I want you to compare that number to what we said our p-value was. It's the same number. So yesterday we had to look it up in the table. And that's probably still the better route to go. But an easier way, if you understand how to enter it in the calculator, you can just do the calculator method. Now, what I'll say for dual credit is on the homeworks, even when it says use technology, you can still use your table. So if you're like, this is kind of confusing on how to enter it, I understand the table, then just use the table. You can just ignore what I just said. For AP, this would probably be good to know for the AP test. It might save you a little bit of time just flipping through your packet there, trying to find the correct number in the table or tracing it. Because if we just kind of explore this for a second, it can even do the inverse normal. So it can, if you put in a probability, it can give you the z-score back. So I mean, like, let's do one that we know already. Let's say we want the area to be 0.05. And y'all don't have to do this, you can. Let's say we want the area to be 0.05. Mu 0, sigma 1. Boom, negative 1.645. That number sounds familiar, doesn't it? Yeah. So, I'll calculate the tricks for you. We're going to use it on these examples today. Like I said, though, for dual credit, you don't have to know how to do this. It just might make your life a little bit easier. Okay, on to the notes for today. So, the past 2 days, we've been looking at hypothesis tests for a population proportion. Today, we're going to look at the test for a population mean. So, to do that, let's review the assumptions that we had to use for a confidence interval for a population mean. There were 3 assumptions we had to make. The first one, we had to assume that X bar is the sample mean from a random sample. Then we had to assume that the sample size n is large, meaning that n is greater than or equal to 30. And last but not least, we either knew sigma or we didn't. We either knew the population standard deviation or we didn't know it. If we knew it, which would we use, Z or T? If it's known, we use Z. If it's unknown, we use T. That's what this is saying down here. So this is the test statistic that we would use if sigma is known. Just do Z equals X bar minus mu divided by sigma over the square root of n. And then the p-value would be the area under the z-curve. Now, here's what I'll say as far as dual credit goes on this. This method is what we would use for the 7.2 homework for dual credit. And on y'all's 7.2 homework, you'll have to know how to do both the p-value method and the rejection region method. Both methods. Remember, the rejection region is where we find the critical value, and then that's where yesterday I was comparing it to touchdowns. If it's in the region, you reject. If it's not in the region, you double reject. P-values, that's where you have to actually use your z-tables and find probabilities. Okay, now if sigma is unknown, then we already said we had to use a t-statistic. And the p-value is the area under the t-curve with n minus 1 degrees of freedom. Now, for dual credit, this one, this is going to be the 7th back. This is going to be the 7.3 homework. Now, on the 7.3 homework, you'll just have to worry about the rejection region method. So you only have to worry about one method on the 7-3 homework. We're on page 11. No. I did show them how to do some calculator though. You missed that part. So what?
Did you write it down up there? How to use it?
I'll work some examples with it, so then you can do it. It's not really something that for y'all, it's imperative to know. It just may save a little bit of time. On y'all's homework, though, you can use the tables all the way through. You don't have to know the calculator trick. Okay. So for this section, since Z is really, I don't want to say it's self-explanatory, but we've done Z tests last section. That's all we dealt with Z tests. So that part really doesn't change much. You're just, instead of doing proportions, you're using means. So this section, we're going to focus on the t-test. Our null hypothesis is that mu equals our hypothesized value. Or if you're dual credit, this could be equals, it could be greater than or equal to, or less than or equal to. As long as it's got the equal to in there, you're good. Okay, so our test statistic using a t-test, we already wrote it down once, but just to write it down again, where we have the procedure all in one spot. Use t equals x bar minus mu divided by s over the square root of n.
What the capital is?
It could be a capital, it could be a lowercase.
Oh, it doesn't matter.
Usually it's a lowercase. On your calculator, though, they have it as capital, so. S, remember, stands for sample standard deviation.
Would you ever see sigma subscript?
It usually is just S. Yeah, it's just standard notation. Sigma is reserved for population. Okay, so for our alternative hypotheses, we have three cases. Either mu is greater than the hypothesized value. In that case, it's a right-tailed test. We're interested in calculating the area in the right tail with our t in degrees of freedom. If mu is less than the hypothesized value, we have a left-tailed test. And if we're not equal to, it's a two-tailed test. So you find the area in one tail, Multiply by 2, that gets you to 2/12. Questions on this so far? Okay, so we have two assumptions we need to look out for. First one is that X bar and S come from a random sample. And also, the sample size N must either be large or the population has to be at least approximately normal. Riley, is Julissa absent?
Yeah, she's not here.
I have that.
Oh, she signed up.
Gotcha. And I saw just you come in. I'm like, she's probably absent.
Yeah, no, she had to leave. But she'll be back tomorrow.
Okay.
Is that all right? So is it always going to be N is greater than or equal to 30? I can dual credit, like it's large. Or is it going to be like a low number?
That'll be 30.
What's the one if it's like 5 for us?
That's proportion.
Portion 5% for us.
Ah. And anyone remember the reason why we say large is greater than or equal to 30? There's something we talked about briefly. Starts with a C. Has the initial CLT. Central limit theorem. That's why we say greater than or equal to 30. Because of the central limit theorem. If we don't have that, then we have to check to make sure it's at least approximately normal. Okay, so let's look at our first example. A study conducted by researchers at Penn State investigated whether time perception, an indication of a person's ability to concentrate, is impaired during nicotine withdrawal. I'm impaired anyways. I never know how much time goes by. After a 24-hour smoking abstinence, 20 smokers were asked to estimate how much time elapsed during a 45-second period. Researchers wanted to see whether smoking abstinence had a negative impact on time perception, causing elapsed time to be overestimated. Where's my little pen at? There it is. So we're interested in it being overestimated. Suppose the resulting data on perceived elapsed time in seconds were as follows. They give us all the data. What can we do to find the mean and standard deviation of this sample? What should we do? Put it in the calculator and run one variable stats. Let's do that. Calculator, one variable stats.
L1, right?
Yes.
Yeah.
As soon as someone gets it, spill the beans, please. X bar is 59.3. And what about S? 9.836. And what about N? Okay, so we got our information from our data. Now, before we go to the next screen, let's go and inform our hypotheses. N wouldn't be large, that's right. But remember, we said N is large or is at least normal. So we're going to actually get to that. We're just forming our hypotheses. So let's write it over here. Okay, so we want elapsed time to be overestimated. So what hypothesis would this go towards? Alternative. Mu has to be what? Mu is greater than 45, which means our null is mu is what? Yep. Or if you're an AP, it would be equal to. So still credits less than or equal to, AP is equal to. Okay, and what's mu? I guess we should define that. True mean. Let's see, what did I say here? True mean perceived time elapsed. And I made it more elegant. See the more elegant version on the next slide. This is just a rough, jotting it down. Okay, so we did that. So there's our more elegant definition for mu. Mu is the true mean perceived elapsed time for smokers who abstain from smoking for 24 hours. That's a mouthful. Okay, so before we run the test, we need to check our assumptions. So I'll give us a hint. The problem doesn't say it's a random sample, but why would I have our first example not be a random sample? So we're going to assume this is random. So it's reasonable to believe that the sample of smokers is representative of all smokers. I asked third period this, and they didn't really seem to have an answer for me. Let's see how much y'all remember. What's the reason we just keep harping on random sample, random sample, random sample? Bias. If it's not random, that means we're introducing bias. Good. I'm hoping third period remembered that. They just didn't want to say it. Okay, and as Nate already mentioned, wait a minute, our sample size is not 30. We don't have a large sample. So we must determine if it's plausible that the population distribution is approximately normal. There's two methods we could use to do this. We can either do a box plot or a normal probability plot. Let's do the box plot. So if we look at a box plot of the data, Notice it looks approximately symmetrical. Not perfect, but it's approximately symmetric. So since the box plot is approximately symmetrical, then it is plausible that the population distribution is indeed approximately normal. Anyone still trying to write it down?
Okay. About done.
Okay. So once we check our assumptions, we can actually start calculating our test statistic. If you're done writing this down, I want you to start calculating your test statistic. And if you got your statistic, what did you get? 6.501, right? Okay. That's what they got too. Good. So now we need to get our p-value. Now, if you're dual credit, you're like, okay, well, I got my test statistic. Can I just look on the table here? On the table, the T table. Well, there's only one problem with that. Do we know alpha yet? Does the problem tell us alpha? No. So we're going to have to use our calculator. And to do that, though, we need degrees of freedom. Now, how many degrees of freedom would this have? 19 degrees of freedom. So at this point, I'm going to switch over to the calculator. And let's, well, before we do that, what kind of test is this? Which tail are we looking at? It's a right-tailed test. So for the p-value, what we're really wanting to find is the probability that t is greater than 6.501 when we have 19 degrees of freedom. Let's take that and go to our calculators and see how to do it in there. So this, Riley, is kind of what I showed them when you were out. I just showed them using the normal distribution. We're going to do the t-distribution. Okay, so on the calculator, how did I get all those distributions? Let's see how much I'll remember. Second, bars.
Can I write this down for this problem?
You may want to, unless you have your calculator and you can practice with us. So second and then bars. And then we want the t distribution. So I need to make sure I pick the CDF because that actually gets us area. I think I said this earlier. The PDF just gets us a point, that point useless. We need area, so we're going to do CDF. Let's go to 6, option 6. And then, let's see, what if we want? We need the probability that t is greater than 6.501. So that means 6.501 would be our lower bound because we want to be greater than that. For the upper bound, we just need a big number. So I'm going to just say, 90 sounds good. And then for degrees of freedom, what did we say? 19. And we'll come down here to paste. Hit enter.
You said you just kind of make up a bigger number?
Yeah. 999 is just a big number we made up. The smallest we can be, since we want to see a greater than a certain number, the smallest we can be is that 6.501. But we can go on forever. And once we get it in here, hit enter and see what we get. Oh, that's a lovely number. Anyone know what it means when it gives you that e to the negative 6? You gotta move the decimal place which direction? To the left 6 times. So what this number really looks like is 0.000157517. That's what this number really looks like. What's our p-value essentially here? What can we might as well say it is? 0. This is our p-value, which we might as well say it's 0. So let's go back to the PowerPoint so we can say that. P-value is, I'm not going to say equals because it's not exactly equal to 0. It's approximately 0. Which means that no matter what alpha we picked, what will we do to this test? Okay. We would reject. I mean, it says use alpha is 0.05, even if I use 0.01. We're going to have to reject. So let's conclude down here. There it is. Since the p-value is less than alpha, we reject H naught. Now, which one of these was our claim in the problem? Was H naught the claim, or was the alternative the claim? The alternative was our claim. So if we reject H naught, that means we're saying that's supported. We can say there is sufficient evidence to support the claim that I'm just going to keep it simple here and say mu is greater than 45. Remember, mu is really, what I really should say if I want to be like totally correct and on the AP test, I wouldn't say the claim that mu is greater than 45. I would say the claim that the true mean perceived elapsed time for smokers who abstain from smoking for 24 hours is greater than 45. I would actually say what mu is in this conclusion here. Does that make sense? I'm trying to split the wording here between what AP wants and what dual credit's going to see on their assignment. So,
Why do these have so much, like, why do these problems have so much, like, entailed in them?
really, as far as calculations go, there's not many calculations. We're just a lot of steps, a lot of wording, and check this, check that. Okay, compute real quick. Now let's write a paragraph to conclude.
We're gonna have to do that on the test.
You'll have to write a statement saying, like all statement would be like what I had up there. Since this occurs, we reject the null. There is or is not enough evidence to reject or support the claim. It'll be like what's on the homework. Yeah. Hopefully I'll figure that out by now. The tests look like the homework.
Mm-hmm.
Questions on this one? Okay, next one. I'm going to skip this part. Okay, so growing concern of employers is time spent in activities like surfing the internet and emailing friends during work hours. Who has time to do that? That's my question. The San Luis Obispo Tribune summarized the findings of a large survey of workers in an article that ran under the headline, "Who goofs off more than 2 hours a day?" Most workers, survey says. Suppose the CEO of a large company wants to determine whether the average amount of wasted time in an 8-hour day for employees of her company is less than the reported 120 minutes. Less than the reported 120. Each person in a random sample of 10 employees was contacted and asked about their daily wasted time at work. The resulting data are the following. So first, let's put this into L1 and get the mean and standard deviation. Let's put this into L1. Then once you get the mean and standard deviation, let me know.
Work 116.8.
116.8, perfect.
And then you get being 448.
Well, let's see here. You said X bar is 116.8. Standard deviation is S should be 9.449. And then N is good. So let's make our null and alternative hypotheses. So she wants to see if her employees are better than the report. So that means what she's wanting to see is if less than the 120 minutes are wasted. So what would that be, the null or the alternative? This is the alternative, that's right. The mu is less than 120, which means the null is what? Equal to. Or if your AP, it would be strictly equal to. And what is mu?
Average mean.
So it's the true mean wasted time per day while at work. Okay, so before we actually run the test, what do we need to check? Our assumptions. So it tells us it comes from a random sample. We're good there. It says it's a random sample, we're good. But now we need to determine, is it plausible that the distribution is approximately normal? So we have two options. We could do a normal probability plot or a box plot. What do we notice about this box plot? It's not completely symmetric, but we can still say plausible, but it's normal. There's no outliers, so it does have some skewness. But maybe if we get a bigger sample, it could be normal. If we just had unlimited time in the world, we would probably want to do a normal probability plot too, just to double check. The box plot does show some skewness. Okay, so let's actually run our test now. Let's calculate t. We said x bar was 116.8 minus 120 over 9.449 over the square root of 10. So calculate that right click and see what you get. So what do we get for our t statistic? Negative 1.07. Perfect. Okay, what kind of test is this based on our alternative? The left tail. So to get the p-value, we need to find the probability that t is less than negative 1.07. What degrees of freedom would we have? 9. Okay, so with that, let's go to our calculator. Plug in 9 degrees of freedom. And our range of values that we want. Clear that out. Okay, so second bars go to the TCDF. Let's see, I want to be less than negative 1.07. So on my low end, I can go as far down as I want, but I can't go higher than negative 1.07. And I'm going to have 9 degrees of freedom. If I do this, I get approximately what? 0.156. So that would be my true p-value. Now, what I'll say is on the PowerPoint, it's going to be slightly off because they use the table here. You want me to count it off, but keep in mind here on the table, it only gives you critical values. What you would have to do is you would have to look for 9 degrees of freedom and then try to see which critical value this got the closest to. Does that make sense? Okay, so they'll give us an alpha level here. But if I use 0.05 as my alpha, 0.05 and 0.156. I explain again how to find P in the table. Yeah, let me open up the table right quick. It's kind of a little weird, but I can try my best to explain it. Let me open the table up and I'll show y'all how to get it. I'm going to use the AP formula chart just because that's the one that I have readily available. Okay, so what we would need to do, go to our T table. And how many degrees of freedom did I have? 9. So whether you're in AP or dual credit, you would still find on your T distribution table 9 degrees of freedom. This is the row I only want to look at. Now, I want to try to find the value that's closest to my test statistic. So, which one of these values in this row is closest to my test statistic? Well, keep in mind we're symmetric here, so there are negatives in front of all of them. If I throw a negative in front of the 1.1, it would be the closest. What's that probability up here? I'm tracing it to the top. 0.15. Good. Notice that's actually what the PowerPoint says is your p-value, about 0.15. Does that make sense? Thank you for asking. So those of y'all here face to face, did that make sense how I found that? Okay. That's two ways you could do it. You could do it on the calculator, or you could do it with a table. They evidently use the table here because, as we can see, our values are a little different. Calculator gave us exact, table gave us approximate.
Would we be wrong in like the homework or anything like that if we did it like a different way on either of those?
On y'all's homework for where you have to do the T statistic, you actually can get away with using the table. You don't even have to use your calculator. Y'all can get away with just using the tables. That's actually what I would recommend because you're going to have to use the rejection region method. So that's what I would recommend is using the table. So for dual credit, just use the table. You won't have to get p-values if you're doing T statistics. Okay. So since the p-value is greater than alpha, what do we conclude? Fail to reject. If we're greater, we fail to reject. Now, which one of these was her original claim? Which one was the CEO's original claim? Less than 120. This is her original claim. So if we fail to reject, is there enough data to support her original claim? No. There is not enough evidence to support the original or I should say the CEO's claim. The CEO's claim. Questions on this one? Yeah.
So if its value is greater than the alpha, that means that delta is less than the alpha. This is the
Yes. Well. Okay, let's flip over then to the next example. one would go a little quicker because we don't have to calculate anything. They actually give it to us. And I'm going to do this one like how Dormit would do it on their homework. And so we're going to use the rejection region method here. Okay, so a manufacturer of a special bolt requires that this type of bolt have a mean shearing strength in excess of 110 pounds. To determine if the manufacturer's bolts meet the required standards, a sample of 25 bolts was obtained and tested. The sample mean was 112.7. So this 112.7 is X bar. And the sample standard deviation was 9.62, sorry. There's S. Use this information to perform an appropriate hypothesis test with a significance of 0.05. This 0.05 is our alpha. Where's N at? I guess I missed N. Which one?
25 billion.
Oh, yep, there it is. 25. Okay, so let's get our null and alternative hypotheses.
105 is A, right?
Yep. So, remember, we're dealing with means here, so we're going to have mu. What is, if I have to have strength in excess of 110 pounds, what would that one be? Alternative would have to be what? Mu is greater than 110, which means the null is, or your AP just equal to. And keep in mind that mu is the true mean shearing strength. Question so far?
Oh, yes, sir. So, why would it be greater than 110?
Because
What does it mean by in excess of 110?
in excess means over 110.
Okay.
Yep. Okay. So let's go to the next slide. We did that. We need. Okay, yeah. Let's calculate. So I just summarized everything here. We're not going to do it the dual. We're going to do it the dual credit way, not the AP way. What do they want our alpha to be? 105. Now, how many tail tests would this be? We keep in mind our null and our alternative. The null is that mu is less than or equal to 110. The alternative is mu is greater than 110. This is right tail, so it's a one tail test, right? So one tail test with alpha equal to 0.05. What are our our degrees of freedom? 24. Okay, so that means our critical value I'm going to put up here, this is the DC way. For our critical value, we need to look in our t-table. And unfortunately, I'll have the credit one readily accessible. Actually, I lied. Give me a second. Gotta sign back in. Dang it. Content. Okay, so let's see. We said it's a how many tell test? One tell. So which column would I use what's my alpha for it? It's a one tell test. What's the alpha? 105. So I'm going to use the second column. How many degrees of freedom? 24. So look down here until you get to 24. What's your critical value? 1.711. Perfect. So it's right there. So the critical value is that T, on the homework they use T naught. That's equal, what we say, 1.711. I'll go with. Okay. So now let's compute our test statistic. So, hang on. I guess before we do that, that means we need to do our rejection region. So we're going to reject if T, want to be, our alternative says greater. So if T is greater than 1.711, then we reject. But let's calculate our T. It'll be X bar minus the mean divided by S over the square root of N. And what would this give us? $1.403. Okay. So how does our T compare to our rejection region? Is T in the region? No. So we're not in the region, which means we do what? We fail to reject. So there is not enough. There is not sufficient evidence to support our claim. Remember, we want it to be This is what we want. That's our claim. So there's not sufficient evidence to support our claim. The bolts don't meet the requirements. That's right. Which means we're going to have to shut down the plant to recalibrate. Questions on this one? Which method do y'all think is easier, the p-value method or the rejection region? Rejection, that's kind of what I think too. Okay. Last example. Hopefully we can fit it in. So I want y'all to, as quick as y'all can, plug this into the one variable stats and get us our X bar, standard deviation, and sample size. Okay, what do I get for X bar? 07798. We can make 798. What about our standard deviation? 0025. Now N? 16. Okay, so this jeweler wants 0.08 ounces of gold. So what should our null hypothesis be? The mean equals what? 0.08. And the alternative is that what? That it doesn't equal 0.08. And keep in mind here that mu is the true mean weight of gold. Okay, so while we're on the screen, let's just make note of a couple of other things. What's our alpha? 0.01. What's our degrees of freedom? And what kind of test is this? One-tailed or two-tailed? This is a two-tailed. Okay, so we got quite a bit of information just from the problem. Let's check our assumptions before we proceed right quick. So we did that, we did that, we did that. Yep, we got it. The mini tab was used to produce this normal probability plot, which is down there at the bottom of your page. And if we notice, most of our points are along the straight line. So what can we assume then? We can assume normality. Good. We're also going to assume that they're randomly chosen. If we look at like a box plot, the reason we went on with the normal probability plot is because we have outliers on our box plot. So we're like, okay, well, maybe, maybe not. But the normal probability plot told us we're good to go. So let's calculate our test statistic here. So t equals, what did we say, 0.07798 minus 0.08 over 0.0025 divided by the square root of 16. Now, no, we're in a crunch for time. We only have like 6 minutes left. So I'll go on and tell you that you should get approximately negative 3.21. Oh, well. So if we did this in the calculator and got the p-value, well, the p-value on this side, the p-value on the left side is 0.003. Now, this is a two-tailed test, so what do I have to do to that p-value? Multiply by 2. Because we have a two-tailed test. This is only the left side p-value. So total p-value is 0.006. What was alpha? 0.01. So how does the p-value compare to alpha? When p-value is less than alpha, what do we do? We reject H naught. So there is, remember, H naught in our case was our claim because he wanted it equal. So there is not sufficient evidence to support I should say is sufficient evidence to reject the claim. There is sufficient evidence to reject the claim mu equals 0.08. Done. Just barely, but done.